Welcome to The Explainer. Look, if you're a software developer, chances are you spent the last couple of years really mastering the art of the prompt. But what if I told you that manual AI prompting, sitting there feeding an agent instructions line by line, is rapidly becoming an outdated bottleneck? Today, we're exploring a massive shift in how we build software. We're moving from just directing agents to actually designing systems that manage them for us.
Let's think about your day-to-day workflow for a second. Are you still stuck playing the role of a manual, turn-by-turn clock inside the AI feedback loop? You write a prompt, wait for the generation, read the output, write the next prompt, and just repeat the whole shebang. You are literally the engine of that process. But what if you could step outside that loop entirely?
And this isn't just theory, right? Boris Cherny, the head of Claude Code over at Anthropic, publicly stated, "I don't prompt Claude anymore. I have loops running that prompt Claude and figuring out what to do. My job is to write loops." Open source leaders like Peter Steinberger are echoing the exact same sentiment. The leverage point is completely moved. It's shifted from writing the words for the model to writing the systems that feed the model.
So, here's our roadmap for today. We'll trace the AI engineering evolution, break down the 4-layer stack, dissect the 5 mechanical moves of a loop, explore the maker-checker split, and finally, discuss how you actually maintain your engineering autonomy through all this.
Section 1. The AI engineering evolution. Let's look at how equipping the worker evolved into building the factory.
All right, so to understand where we're going, we kind of need to see where we've been. Prompt engineering was our foundation. It's simply the words you write for the model, the tone, the role, the examples, all that good stuff. But structurally, it fundamentally requires you, the human, to be present for every single exchange.
Then we moved a floor up, right? Context engineering. This mine's what goes into the context window right now. It definitely expanded our capability by managing retrieval, summarizing docs, and clearing out stale information so the agent doesn't get confused. But again, the system still just sits there waiting on you to press enter.
Next came harness engineering. This arms a single agent run. It equips the agent with tools, actions, and defines exactly what counts as done. So now the agent can use a browser or a terminal, but it still stops entirely after a single successful run, just waiting for your next command.
And that brings us to the massive shift we're talking about today, loop engineering. This is what automates the waiting for you away. It pulls you out of the machine entirely, automating the downtime, scheduling continuous runs, and feeding its own results back into itself. You literally stop being the engine and become the engine designer.
Section 2, the 4-layer stack. We really need to treat these stages as a cohesive, interlocking software architecture.
What's genuinely fascinating about this whole stack is how it reveals the blast radius of an error. At the prompt layer, a mistake gives you one bad answer and you fix it instantly. But at the loop layer, the system runs while you sleep. A misread assumption gets written to a state file, read back the next morning as fact, and built upon across dozens of turns. The higher the layer, the farther you are from the scene of the crime, and the more dangerous a compounding error becomes.
So, let's nail down our definition here. Loop engineering is the shift from prompting a coding agent turn by turn to actually designing a recursive control system. It's a system that autonomously discovers work, assigns tasks, verifies the results, saves its state, and repeats on a schedule. I can't stress this enough. It is not just writing a bigger prompt.
Section 3. The 5 moves of a loop. Let's break down how this mechanical execution actually works.
Okay, so a working loop absolutely requires mechanical execution across 5 specific moves. First up, discovery. It finds work on its own, like reading CI failures. Second, handoff. It isolates tasks, usually via Git work trees, so parallel agents don't accidentally collide. Third, verification. A sub-agent evaluates the code. Fourth, persistence. It saves its state to a disk file. And fifth, scheduling. It automates the heartbeat so it runs on a regular cadence. If you skip any of these, the entire automated system just breaks down.
Now, disastrous things, and I mean real anti-patterns, emerge when you start skipping these moves. Skip scheduling, and you have a manual loop that stops the second you close your laptop. Skip persistence, and you get an amnesic loop that forgets its progress every single run. But the absolute most dangerous is skipping verification. That creates the nodding loop. This is where an agent writes code, and then that exact same agent praises its own broken code. It just accumulates plausible-looking mistakes at machine speed.
Section 4. The maker-checker split. This is the engine of verification and hands down the most critical move to get right.
We literally have to structurally separate the maker from the checker here. Think about it.
The generator writes the code, but it's fundamentally the worst possible judge of that code because it sees its own chain of self-persuasion. The evaluator, on the other hand, is your ultimate unit test. It uses a totally different model, defaults to heavy doubt, and acts without any modesty whatsoever. This maker-checker principle is decades old in banking, and honestly, it's absolutely mandatory for autonomous agents.
So how exactly do we fix that dangerous nodding loop? Well, by tuning an independent skeptic. It is so much easier to tune a separate sub-agent to be highly critical than it is to make a generating agent critical of its own work. You force the evaluator to act, using tools like Playwright to click buttons and take screenshots, instead of just passively reading the code. You command it to assume the code is broken right out of the gate, and you use a fresh, small model to judge that final stopping condition.
To see what happens when you actually scale this up properly, just look at Stripe's Minions pipeline. They're merging over 1,300 machine-written PRs every single week. That deterministic orchestrator is key. Reliability comes from hard-coded, deterministic gates gathering the context, not just from massive probabilistic LLMs. They keep the rules outside the model. It completely proves that enterprise reliability is about the quality of your constraints, for sure, not just the sheer size of your AI.
Section 5. Staying the engineer. How do we actually utilize these loops without suffering from total cognitive surrender?
Here's the scary part. A loop that runs itself, errs by itself, and it racks up 4 silent costs. Verification debt builds when you merge unverified code. And because you didn't read it, your mental map of the code base decays. That's comprehension rot. That decay naturally invites cognitive surrender, where you just abdicate your judgment and accept whatever the machine says. And because you aren't watching, boom, you suffer a token blowout, as the loop burns your API budget retrying errors all night long. These 4 feed into each other at blazing machine speed.
To defend against all that, you absolutely need a strict operational blueprint. First, read a sample of the loop's output daily, and force yourself to explain it. If you can't, your mental map is rotting. Second, cap your budget, and retries before you ever ship the loop, setting hard circuit breakers to stop runaway costs. Finally, keep one door open. Ensure there is always a manual human checkpoint before a pull request actually merges into production.
All right, here is the absolute core takeaway of this explainer. Loop engineering makes generation nearly free. Code, plans, bug fixes, they all become abundant. But you know what that does? It makes your human judgment the only genuinely scarce and valuable resource left in the entire workflow. You have to build a loop like someone who intends to stay the engineer, not just a person who presses go. Because, listen, the exact same loop built by 2 different people can have completely opposite outcomes. One developer uses it to scale their judgment. Another uses it to abdicate their understanding entirely. So as we wrap up today, I'll leave you with this. As you start building these automated systems, will you use them to amplify your engineering expertise, or will you let them hollow it out? The choice is entirely in how you design your loop.